Hello, my people. How are we? Um, Now, just by way of review, we discussed this briefly in our time together on Friday, but I want to make sure that we understand this. You remember those really obnoxious SAT questions where they had geometric shapes and you were supposed to find the area of the shaded region? Okay. And basically, it winds up being a simple case of subtraction. Okay, you need to figure out the area of the whole and subtract the area of the whole. Well, that's going to be precisely what we're doing here. Now, if we have simply a circle with a circle cut out, and this is actually a picture of a washer, I basically, if I identify the center, I can figure out the fact that I have one radius right here. I have a large radius. Let me get a larger pen to represent that. Okay. I have a large radius and I have a small radius. Okay. This large radius right here is big R. This small radius is small r, okay? So the area of the entire thing, including everything, would be the area of the whole, W-H-O-L-E, and it would be pi big R squared. Now, in order to get just the shaded region, I need to cut out that little bit right there. So what is the area of that? What is the area of the whole? H-O-L-E, that would be pi small r squared. Okay. Now, when we're dealing with washers, you have to remember that it's just a prism, right? A cylinder is a prism, and it's pi r squared h. Okay. A washer is basically a cylinder where a smaller cylinder has been pulled out. So it's very similar to what we're doing right here, and as long as I can identify big R and small r, I should be able to do the same thing because the volume of a washer should be nothing more than the area of the base times the height. And of course, the height or width, depending on which orientation we're dealing with, is simply my differential, right? It's that infinitesimal width, either the dx or the dy. Now, in this particular case, remember that this is big R because it's the larger one, and that's small r. And so the volume of the whole is pi r squared h. And the volume of the small one is pi small r squared h. Now, the great thing about this is that they both include pi and h. Now, of course, my h winds up being my differential, so it's really dx. And so basically what happens is I can actually pull out pi and the h and get r squared minus r squared. And that's what's going to happen here. Okay, that's what's going to happen when I'm dealing with taking these geometric principles and applying them to the integrand, because I know that really all I have been doing with the disk method is taking cylinders of infinitesimal width, an infinite number of them, and just summing them up, accumulating them, right? What I'm going to be doing here is something very similar. I just have to figure out the volume of the whole and subtract the volume of the whole. So let's go ahead, and we're going to return to one of the functions that we dealt with earlier, 4x minus x squared, but we're going to pair it with x minus 2 squared. Okay, and the axis of revolution we're going to do it around is the x-axis. Okay. Now, we'll go ahead and use that customary scaling of 2 boxes is equal to a single unit. So my Cartesian plane here goes from -5 to 5, -5 to 5. I know, because I've already graphed it before, that my 4x minus x squared looks something like this. Okay. Now, let's go ahead and we'll make that one pink. Now, my second function should be even easier to graph, right? It is just the parent function moved over 2 units. So here's my vertex. I go over 1, up 1. I go over 2, up 4. And the same thing on the left-hand side. And I notice that these intersect, okay, here and here. So those points of intersection are going to wind up being very useful because those are going to be our limits of integration. So first order of business, once I've completed my pretty picture right here, is to go ahead and find those. So this is the region that we're dealing with, okay, and we are going to be revolving it around the x-axis. And my cross sections, despite the fact that this area, this region, is not flush against the axis of revolution, are still perpendicular to it, okay? And therefore, I know that my width is going to be dx, and my limits of integration need to be in terms of x as well. Well, let's go ahead and figure out what those are. 4x minus x squared, and I'm going to go ahead and do the x minus 2 in its expanded form. And this winds up being 2x squared minus 8x plus 4. Yeah, well, let's go ahead and divide through by 2 and sort of get it into shape to where it's actually helpful. And I know that by completing the square, I need to add 4 to this side and add 4 to this side. That's going to give me x minus 2 squared is equal to 2, and therefore x is equal to 2 plus or minus root 2. Okay. Now, let's go ahead and leave them like that. We can actually plug it into our calculator in that way, or we can get a decimal approximation. We're obviously going to be using our calculator to find the actual volume, and of course in this one, since there is a bit of symmetry, right? You know, you could cut this right down the middle and do the left half and the right half, do the left half or the right half, and then multiply it by 2. So you could actually, instead of going from 2 minus root 2 to 2 plus root 2, you could go from 2 to 2 plus root 2 and then just multiply that answer by 2. We're not going to do that. Let's go ahead and just set it up as 2 minus root 2, which is 2 minus 1.414. So that's, you know, somewhere in the neighborhood of 0.59. And this is 2 plus root 2, so that's somewhere in the neighborhood of 3.4. I know that I'm going to have pi out in front. Now, I have an inner, meaning an inner and an outer an inner and an outer edge when I start revolving this around, right? That outer edge is my big R, okay? How far is that function away from my x-axis? And the answer is, it is 4x minus x squared away, right? So I'm identifying my big R as 4x minus x squared. And if you need to go over to the side and actually do this, and then do this to remind yourself that it is this that goes in the integrand and not that, then by all means do it. And of course, like I said, squaring it. And I know that my small r is going to be the one that is closest to the axis of revolution, and that is going to be x minus 2 squared. Well, when I square that, it winds up being x minus 2 to the 4th, or if you want to, x squared minus 4x plus 4 squared, right? Because that is, of course, how it expands over here. We're going to be using our calculator, so it really doesn't matter all that much. Let's call it x minus 2 to the 4th, just for giggles, okay? Now, basically after this, any work that is done is just symbolic manipulation. It's just the analytic work, okay? The actual the actual calculus is largely in the conceptual understanding of this is actually in the setting it up. So if you get to here, that's 80% of the points on a particular problem, because that's really what I'm evaluating. It's what I'm assessing when I give you an assessment on something like this. I'm assuming that you know how to integrate. I'm assuming that you know how to do the analytic manipulation in order to get all of that into polynomial form and collect like terms and put it in descending order and then integrate term by term, because that's what's going to happen here if we don't do it by means of our calculator. But we're going to, for the sake of time, do it by means of our calculator. Let's go ahead and put our pi in there, and then we'll plop in the integration. So I can do 2 minus root 2 and 2 2 plus root 2. Okay. Now you got them, and the only thing that is the problem here is, maybe we should have plopped these into our y1 and our y2 to make this work a little bit easier. Let's go see if we can go ahead and do that. Let's get rid of the functions that were there before. Let's see, my first one is 4x minus x squared, and my second one is x minus 2 quantity squared. Now, I really don't care about the graph. Let's go ahead and get back to these parentheses. Now remember, you're going to be squaring these. So it's y1 squared minus y2 squared dx. Okay. Go ahead and press, and we're going to get 94.781 units cubed. Yay! Okay, well, that was all fun. Let's go ahead and move on to the next one. Let's talk about the regions. Define the region first, as always. Y is equal to natural log x. Y is equal to x. Y is equal to 0. And y is equal to 2. Okay. Because it's natural log x, and basically you need to get out to about 7.2 before it even gets up to y is equal to 2 and output of 2. Let's go ahead and leave it as negative 10 to 10 and negative 10 to 10. Remember, natural log goes through that point 1, 0, and then it doesn't go through 1 until e. So about 2.7, it hits e. Right? At 2.7, which is e, it hits an output of 1. And then e squared is somewhere, if memory serves, about 7.2. So 7.2 winds up being that, okay? And so let's go ahead and sketch. I guess we could have changed the scale on y. It's just going to make it a little more difficult when I'm dealing with the identity function with y is equal to x, because we're used to the identity function kind of going straight from corner to corner, unless the scale has been changed. So let's go ahead and color code them. Natural log x. And I haven't done the complete graph of them because the graphing is really not the point. The graphing is only for the sake of being able to visualize, right, the region that I'm dealing with. Now, I also need to deal with y is equal to 0, and that, of course, is the x-axis. And I also need to deal with y is equal to 2, and that is right up here. Now, the region that I have been given is this, in here. All right. Well, what we're going to do is we're going to spin it around the y-axis. Okay. Now, that means that I'm going to have cross sections. I did color it in rather darkly. Let's see if this works. There we go. I'm going to have cross sections, and I can go ahead and zoom in just a little bit more for the sake of being able to visualize this a little bit better. And I'm going to basically spin it around the y-axis. Now, if my if my cross sections perpendicular are horizontal, then I know that it's in terms of y, dy. Well, I can already see very easily that my limits of integration are 0 to 2. So let's go ahead and put down here what we already know, 0 to 2, and then I'm going to need a dy. If I am doing a washer around the y-axis, then big R, of course, just like when I'm doing it around the x-axis, big R is determined by the graph, by the curve that is farthest away. Okay? Y is equal to natural log x is farthest away, but we have a problem. It's y in terms of x, and I need it x in terms of y because I'm going to be integrating along y. But y is equal to natural log x transfers easily enough into x is equal to e to the y. This right here is my big R, and therefore r squared is e to the 2y, okay, by rules of exponents. Now, I know that x is equal to y as my identity function is the same thing as x is equal to y is equal to x. I don't have to change the form, but as I say x is equal to y, I need to identify this as my small r, and therefore r squared is y squared. So I now have both my big R squared and my small r squared in terms of y. I can go ahead and plop them in, e to the 2y minus y squared dy. Now this one isn't too difficult in terms of doing it by hand. I don't have irrational numbers on my limits of integration, and both of the terms in the integrand are I'm perfectly capable of doing. Okay, let's go ahead and do that. So I have pi. Now e to the 2y, like I've said before, is a u sub problem, but because it is composite, but it's so easy that we know that all we would need to do is separate the integrals out and put a 2 in front of the dy and a 1/2 out in front. And e to the 2y times 2 dy is going to give us e to the 2y. You just have to remember the 1/2. The y squared becomes 1/3 y cubed, and I'm going from 0 to 2. Now, the 0 is actually going to matter in this particular one because this is not a polynomial term, and e to the 0 actually does have a value. But let's go ahead and plug in 2 first. I'm going to get 1/2 e to the 4th minus 1/3 times 8, right? Because 2 cubed is 8. Minus 1/2 e to the 0 minus 1/3 times 0. Okay, that term obviously goes bye-bye, but the rest of this actually needs to be, reckoned with. Okay, and it winds up being pi e to the 4th over 2 minus 8/3 minus 1/2. And I can get a decimal approximation for that relatively easily. Let's go ahead and do that. Let's make sure you include all of it, otherwise you're going to forget the pi when you're all done. I know that it's e to the 4th over 2 minus 8 over 3. And this one I can do lazy man style by dealing with it as the decimal equivalent. And I get an approximate answer of 75.814 units cubed. Okay? Now, that takes us to about 20 minutes. I'll wait to hear from you guys if you want me to actually do another video. I have a couple more problems that I can do, and I'll churn out another video upon request. But considering the fact that you have several videos from before, and this is the 4th video from this year, I think that we'll go ahead and call it quits here. If you have any questions, as always, please do let me know. Send me a message, send me an email, and I will do my best to reply promptly. I look forward to seeing you guys on Tuesday when we will talk about the other type of volume that we will be doing, and I actually think those are even cooler than these. So we have that to look forward to. See ya.